Hi, my name is Sloan.
I'm Kaitlyn Bell.
I'm Brian Twiggs.
I'm Chelsea Houston.
And for our 157 project, we made a self-deploying speed bump.
In 2014, 172 work zone fatalities resulted because of speeding vehicles. The motivation of this project was to make installing a portable speed bump easier and faster, so that speed bumps may be more widely implemented in work zone areas. There are currently no self-deploying speed bumps on the market today.
The most important requirement was that it must be able to slow the flow of traffic. With that, the speed bump must remain stationary, support large loads, span a full lane of traffic, be easy to handle using available construction equipment, and deploy in a reasonable amount of time. The engineering targets were set according to these requirements. The max load would be equivalent to 15,000 pounds, have a 12-foot deployed length, but no more than 5 feet when undeployed, be 3.5 inches tall and up to 12 inches wide. It should weigh less than 750 pounds and deploy in less than 3 minutes.
Our self-deploying speed bump consists of 4 speed bump sections connected by 3 connecting rods and 2 guide rails. Bearings located in the wheels and connecting rod pins help to extend the life of this speed bump. To deploy, wheels driven by motors located in the final speed bump section pull the assembly down. To prevent toggle positions in the connecting rods while the speed bump is in its deployed state, the connecting rod pins are offset. With this, the connecting rods are angled down slightly. To return to the undeployed state, the motors run in reverse, pushing the speed bump sections back up. This motion is assisted by torsion springs located in the first speed bump section. In its deployed state, our speed bump is 12.5 feet long, 16 inches wide, and 3.8 inches tall. In its undeployed state, the speed bump is just under 5 feet long and 2.7 feet tall. With a chosen material of 661 aluminum, the final weight is 460 pounds.
The static loading simulations fall into 2 categories: simulations over the solid section of the speed bump and simulations over the gap in the center of the speed bump. For all static loading simulations, a weight of 62.3 kilonewtons and a tire contact area of 185 millimeters by 127 millimeters was assumed. This simulated a single tire bearing all the load. For the solid section simulations, the maximum von Mises stress was 2.2 megapascals, which leads to a factor of safety of 126. The maximum deflection was 2.6 micrometers. For the simulations over the gap, the contact area between the tire and the speed bump is reduced, since some of the tire is over the gap. The highest stress and lowest safety factor was on the mover section of the speed bump. The von Mises stress was 5.6 megapascals, and the minimum safety factor was 48. The maximum deflection was 8.3 micrometers.
Due to the weight of the bump members, all pins have a safety factor of 423, and connecting rods have safety factors over 5,000. To assist in deploying and undeploying, 2 torsion springs and 7 bearings were added to the system. The torsion spring variables were calculated and selected so that a suitable safety factor of 1.79 and 1.65 for fatigue and yielding were achieved. Bearings were selected to achieve a safety factor of 1.7.